The interstellar object 3I Atlas is once again forcing scientists to stop and take a closer look. In its latest observations, the Hubble Space Telescope examined deep into the object's core and recorded something that is almost impossible to ignore. 3 narrow, sharply defined jets are erupting from the center, arranged in a near-perfect equilateral triangle, separated by angles of roughly 120 degrees. It is a level of balance that is difficult to believe could happen by chance. This single detail led astronomer Avi Loeb to make a controversial claim. He argues that this may not be just a natural anomaly, but a possible sign of extraterrestrial technology. But before you rush to accept or reject that idea, watch until the end, because what 3I Atlas is revealing may go far beyond our first assumptions. 3I Atlas is not just another object drifting quietly through space. From the moment astronomers detected it, its path alone signaled that something was different. Unlike most comets, 3I Atlas follows a hyperbolic trajectory, which means it is not trapped by the sun's gravity and will never return once it leaves. This detail immediately places it outside the family of objects that formed within our solar system. 3I Atlas was shaped around another star, in an environment we cannot observe directly, and then thrown into interstellar space long before Earth even existed. That journey alone makes it rare, but rarity is not what unsettles scientists. What matters is how 3I Atlas behaves after entering the inner solar system. To understand this, researchers quickly compared it with the 2 interstellar visitors observed before it. The first was Oumuamua, discovered in 2017, an object that showed no clear dust tail yet experienced unexplained acceleration as it moved away from the sun. That behavior triggered years of debate and never reached a final agreement. The second was Borisov, detected in 2019, which behaved much more like a traditional comet, releasing gas and dust in familiar ways. 3I Atlas does not align cleanly with either example. It shows strong activity, yet not in the chaotic and uneven pattern scientists usually expect. It is also large by interstellar standards, which provides richer data but also increases uncertainty. As it approaches the sun, 3I Atlas does not simply heat up and shed material from random weak points. Its reactions appear steady, organized, and difficult to explain with a single natural process. What makes this especially striking is that these unusual traits do not appear in isolation. They appear together, reinforcing one another. The foreign trajectory, persistent activity, and internal consistency all point toward an object that resists easy classification. This combination is why 3I Atlas quickly became a priority target for multiple observatories. Scientists are not merely tracking another comet. They are studying a physical sample from another star system that refuses to behave like anything already known. Every observation window matters, because once 3I Atlas exits the solar system, this opportunity disappears forever. With that urgency in mind, attention soon shifted from its path to the details hidden beneath its dusty exterior, where new image processing methods began to reveal structures no one expected to see. When attention turned from trajectory to structure, scientists relied on one instrument capable of seeing through confusion. The Hubble Space Telescope was tasked with observing 3I Atlas during a critical window late in the year when activity near the sun made the object bright but visually complex. Over multiple sessions, Hubble captured a sequence of high-resolution images as the object moved against a background of distant stars. At first glance, the raw data looked unremarkable. The images showed a diffuse white blur surrounded by haze, a familiar sight to anyone who has studied active comets. That blur was the coma, a thick cloud of gas and dust released as solar heat reached frozen material near the surface. For most objects, the coma hides more than it reveals. Fine dust scatters light in all directions, masking any internal structure and turning the nucleus into a featureless glow. If analysis stopped there, 3I Atlas would have appeared ordinary, but astronomers do not stop at first impressions. To look deeper, researchers applied a specialized image processing technique known as the Larsen-Ciacchinina rotation gradient filter. This method removes static brightness and highlights changes linked to rotation and motion. Instead of asking how bright the object is, it asks how that brightness shifts from one frame to the next. When the filter was applied, the coma faded into the background. What remained was not noise, but structure. Emerging from near the core of 3I Atlas were three narrow streams of material, sharply defined and persistent across multiple observations. These were not scattered bursts or short-lived flashes. They were stable jets, extending outward with clear direction and consistent intensity. Even more striking was where they originated. The jets did not appear at random distances within the coma. They traced back toward the same central region, close to the nucleus itself. This matters because jets formed near the core reflect internal processes rather than surface accidents. In typical comets, vents open and close as sunlight reaches uneven terrain. Those outflows wander, weaken, and shift as rotation changes exposure. The jets seen in 3I Atlas did not behave that way. They held their shape across time and did not blur into the surrounding dust. This suggested a controlled release of material rather than a chaotic response to heating. Researchers confirmed the pattern by checking multiple image sets taken on different nights. The same structures appeared again and again. That repetition ruled out random dust clumps or temporary imaging artifacts. It also ruled out background stars or processing errors. What Hubble was revealing was a real physical arrangement inside the coma. At this stage, scientists avoided bold claims. They focused on what could be stated with confidence. There were three jets. They were narrow, stable, and linked to the inner region of the object. They were not evenly smeared by rotation. They were not drifting with solar wind. They were behaving as if anchored to something beneath the dust. That realization changed the tone of the investigation. The question was no longer whether 3I Atlas was active. The focus shifted to how such ordered structures could exist inside an object assumed to be irregular and fragile. With the dust stripped away by careful processing, the next step was unavoidable. Scientists now had to measure the geometry of what they were seeing, because the spacing between these jets carried implications far beyond simple comet activity. Once the jets inside 3I Atlas were confirmed as real physical structures, attention shifted to their arrangement. This step mattered because shape is not decoration in space, but evidence of underlying forces. When researchers measured the angles between the three jets, the result immediately stood out. Each jet was separated from the others by roughly 120 degrees. Together, they formed a near-perfect equilateral triangle centered on the core of the object. In simple terms, the jets were spaced as evenly as possible around a circle. This kind of balance is easy to recognize, even without advanced mathematics. It is the same geometry used when equal force must be spread evenly to prevent wobble. In engineering, this arrangement appears in rotating systems, stabilizers, and propulsion designs. In nature, especially at the scale of a comet, it is extremely uncommon. Most comets release gas through cracks, weak spots, and uneven layers in their surface. Those vents are shaped by impacts, erosion, and internal stress over billions of years. As a result, natural jets usually appear in messy clusters or shift position over time. They rarely stay fixed and almost never line up with geometric precision. This is where probability enters the discussion. Scientists asked how likely it would be for three independent vents to appear naturally at equal spacing. They also considered whether those vents could remain active at the same time with similar strength. When these factors were combined, the odds dropped sharply. The estimated probability settled around 1 chance in 500. That number does not claim impossibility. It signals rarity at a level that demands explanation. To make this easier to picture, imagine throwing 3 objects at a wall without aiming. Now imagine them landing in a balanced triangle. Then imagine that pattern repeating every time the object rotates. That is the challenge scientists faced when looking at 3-eye atlas. Probability alone does not prove intent, but it changes how evidence is weighed. In science, unlikely patterns force researchers to question assumptions rather than ignore them. Some teams suggested that rotation might be shaping the outflows. Others proposed that internal layering could guide gas along preferred paths. These ideas were noted, but they carried limits. Rotation can smear patterns, but it does not usually create symmetry this clean. Internal layers can guide flow, but they rarely align so evenly without disruption. The geometry remained stubbornly consistent across observations. That consistency was the key issue. A single snapshot could be dismissed as coincidence. Repeated alignment across time could not. The triangle inside 3-eye atlas was not drifting, collapsing, or reshaping itself. It behaved as if locked into place. At this stage, researchers avoided dramatic conclusions. They focused on what the data allowed them to say. The structure was balanced, the spacing was precise, the probability was low. Together, those facts placed 3-eye atlas outside comfortable expectations. With geometry now firmly in view, attention began to move beyond shape alone. Scientists started examining whether the chemistry and motion of the object supported or challenged what the angles were already suggesting. Once the geometric pattern inside 3-eye atlas was established, scientists turned to chemistry to see whether the material itself told the same story. Spectroscopic observations revealed an unexpected signal coming from the coma. Nickel was present in clear and measurable amounts. What made this result stand out was what did not appear alongside it. Iron was nearly absent. In known comets, nickel and iron almost always appear together because they form and bond under similar conditions. Separating one from the other requires unusual environments or long and selective processes. For 3-eye atlas, the imbalance was not subtle. The nickel signal was strong enough to rule out contamination or noise. This forced researchers to consider chemical pathways that are rarely discussed in comet studies. The anomaly did not end there. As observations continued, scientists noticed that material from 3-eye atlas was not flowing in the expected direction. Instead of streaming away from the sun, one of its dominant jets pointed directly toward it. This behavior was confirmed by multiple instruments and viewing angles. It could not be explained by perspective or background effects. In standard comet physics, sunlight heats surface ice and pushes gas outward, forming a tail that always points away from the sun. A sunward jet contradicts that basic expectation. To explore this further, researchers analyzed the composition of the ejected material. Carbon dioxide dominated the outflow. The ratio of carbon dioxide to water vapor was unusually high compared to typical comets. Such a composition changes how gas responds to heat and pressure. It also affects how dust grains move once they leave the surface. This offered a partial explanation for the strange jet direction, but it did not resolve everything. Another clue came from polarization data. Light scattered by the dust around 3-eye atlas showed extreme negative polarization. This pattern suggests fine and compact grains rather than fluffy and irregular particles. Compact grains interact with sunlight differently. They can resist being pushed away and may even follow paths that seem counterintuitive. Still, even this explanation had limits. The chemical signals and dust behavior aligned with the geometry already observed. They did not contradict it. Instead, they reinforced the idea that 3-eye atlas was acting as a single system rather than a collection of accidents. To verify these findings, Data from multiple observatories were compared. Infrared measurements from the James Webb Space Telescope supported the presence of carbon-rich gases. Ground-based telescopes confirmed the persistence of the nickel signal over time. No single dataset stood alone. Each added weight to the same conclusion. This was not a one-off chemical fluke. It was a pattern. Geometry, chemistry, and motion were pointing in the same direction. The implications were uncomfortable. If these traits appeared separately, they could be dismissed individually. Appearing together, they demanded a broader explanation. With chemistry and dynamics now matching the strange geometry, attention began shifting to what kind of internal structure could support all of these behaviors at once. As if geometry and chemistry were not enough, 3I Atlas revealed another layer that few scientists expected to detect at all. In early December, astronomers observed faint but measurable X-ray emission coming from the object as it crossed interplanetary space. The detection was made using the XMM Newton, an observatory designed to track energetic signals far beyond the visible spectrum. X-rays are not produced by reflected sunlight, which immediately ruled out simple surface illumination. They also did not come from internal heat, since objects like 3I Atlas are too cold to generate such energy on their own. Instead, the emission originated inside the coma, the cloud of gas surrounding the nucleus. This pointed to an interaction rather than a source. As gas escaped from 3I Atlas, it collided with the solar wind, a stream of charged particles flowing outward from the sun. When those particles met neutral atoms in the coma, electrons jumped between them and released energy as X-rays. This process is known as charge exchange. Scientists have observed charge exchange before in comets formed within the solar system. What made this case different was the origin of the gas involved. The material producing the X-rays in 3I Atlas was not formed near our Sun. It condensed around another star, under different temperatures, pressures, and chemical histories. That difference matters because X-rays are especially sensitive to light elements. Hydrogen and nitrogen play a key role in charge exchange reactions. These elements are central to planetary chemistry and atmospheric evolution. They are also difficult to study using optical or infrared telescopes. Through X-ray measurements, scientists can infer their presence indirectly. The intensity and distribution of the X-ray glow suggested that gas release from 3I Atlas was steady rather than sporadic. The emission did not flare and fade in unpredictable bursts. It appeared consistent across the observation window. This matched earlier evidence that the object was not behaving like a fragile, crumbling body. To place these findings in context, researchers compared 3I Atlas with earlier interstellar visitors. Oumuamua showed unusual acceleration but no visible coma, which made similar X-ray analysis impossible. Borisov behaved like a conventional comet and produced expected signals consistent with solar system chemistry. 3I Atlas occupied a new position between these extremes. It released gas clearly enough to study, yet its composition and behavior did not align with known models. This combination allowed scientists to observe interstellar material interacting with the Sun in real time. The broader implications quickly became clear. If interstellar objects commonly carry different ratios of light elements, current theories of small body formation may be incomplete. Planetary systems around other stars may produce debris with chemical structures rarely seen near the Sun. This would explain why 3I Atlas does not resemble familiar comets despite sharing some outward traits. It may not be an exception, but an early example of a much wider population. Each new detection would then represent a different chemical fingerprint rather than a variation of the same theme. The X-ray data also reinforced a pattern already forming. Geometry, chemistry, motion, and now high-energy interaction all pointed toward internal consistency. Nothing observed so far behaved randomly. Each layer of evidence supported the next. With X-rays added to the picture, 3I Atlas no longer appeared strange in one isolated way. It appeared systematically different. At this point, the investigation moved beyond cataloging anomalies. Scientists began focusing on whether any known natural structure could sustain all of these traits under extreme stress, especially as the object approached the strongest gravitational force it would encounter in its journey. By the time geometry, chemistry, and X-ray emission were confirmed, scientists began to confront the limits of familiar explanations. Several cautious theories were offered to keep the discussion within known physics. One proposal described 3I Atlas as a contact binary, formed when separate bodies gently collided and fused long ago. Such objects exist and can show uneven activity under solar heating. Another explanation focused on rare chemistry shaped by long exposure to radiation in interstellar space. Under this view, unusual emissions could form naturally without requiring anything artificial. These ideas were reasonable, but they left important gaps. A contact binary can explain irregular shape, but it struggles to preserve stable internal balance over time. Exotic chemistry can explain odd signals, but it does not account for persistent symmetry and efficiency. The difficulty was not one anomaly in isolation. It was the way multiple anomalies aligned without canceling each other out. This is where the perspective of Avi Loeb entered the debate. Loeb did not claim that 3I Atlas was a spacecraft. He argued that its structure showed a level of balance that deserved serious attention. He described it as an unusual signature rather than a conclusion. Many researchers pushed back and called for restraint. Extraordinary interpretations require strong evidence. Still, few denied that 3I Atlas was stretching existing models. That tension now leads to a decisive moment. In March 2026, 3I Atlas will pass close to Jupiter. Jupiter's gravity is strong enough to tear apart weak and loosely bound objects. If 3I Atlas is fragile, its structure should distort or collapse during the encounter. If it remains stable, the discussion will change in a fundamental way. This approach transforms debate into observation, where nature itself will determine which explanations can survive. Long before 3I Atlas entered the spotlight, science had already learned that space does not always behave as expected. Across decades of observation, astronomers have repeatedly encountered objects that defied easy explanation. Some appeared briefly and vanished before detailed study was possible. Others left behind data that never fully fit existing models. These encounters slowly changed how scientists think about what moves through the solar system. At NASA, new survey programs were designed to spot fast and faint objects earlier. Wide-field telescopes and automated tracking systems now scan the sky every night. The goal is no longer just discovery, but rapid response. In Europe, European Space Agency expanded its focus on coordinated observation. Rather than relying on a single instrument, ESA links ground-based telescopes with space-based platforms. This approach allows scientists to compare data across wavelengths in real time. Infrared, optical, and X-ray observations now work together instead of separately. Elsewhere, countries such as Japan, China, and India have also increased their capabilities. Each new observatory adds another layer of coverage. Together, they form a global network rather than isolated efforts. This matters because strange objects rarely announce themselves clearly. They reveal their nature only when observed from many angles at once. The rise of powerful data processing has been just as important as new hardware. Modern algorithms can detect subtle motion against crowded star fields. Patterns that once looked like noise can now be flagged within minutes. This is why objects like 3I Atlas receive attention so quickly today. What once took months now happens in days. The broader trend is clear. Science no longer treats anomalies as distractions. They are seen as opportunities to test the limits of existing knowledge. Every strange visitor forces models to stretch or break. Sometimes they break permanently. This process is uncomfortable, but it is how understanding grows. 3i Atlas did not appear in isolation. It arrived at a moment when humanity is finally equipped to watch closely. The investment in technology ensures that even brief visitors can leave lasting evidence. As detection improves, strange objects will no longer be rare events. They will become data points in a much larger pattern. With that shift underway, attention now turns to how these growing capabilities will shape the next encounter that challenges everything we think we know. 3i Atlas entered the solar system as a distant interstellar object, but it did not behave like one. Instead of showing random activity, it revealed structure, balance, and persistence where chaos was expected. Hubble uncovered 3 narrow jets arranged with near-perfect geometric precision. Chemical observations exposed nickel without iron and material moving in directions that defy familiar comet behavior. X-ray emissions added another layer, showing how matter formed around another star interacts with the Sun in real time. None of these signals stand alone. Together, they form a connected pattern that challenges long-held assumptions about natural debris drifting through space. Avi Loeb's interpretation remains controversial, yet it highlights how far this object stretches existing models. The coming encounter with Jupiter in 2026 will subject 3i Atlas to extreme gravitational stress. Whether it breaks apart or holds its structure, the outcome will shape how this visitor is remembered. When 3i Atlas leaves the solar system, it will take its physical presence with it, but the questions it raised will remain, pushing science to look beyond comfortable explanations.